let's dive into a few more examples now related to kind of work energy and power. All right, so here's the first example, which states a medical device is being lowered into place by two mini cranes. So the medical device starts at a height of 285 centimeters above the floor's surface. The medical device has a weight of 1250 pounds, okay, and we'll assume that 1 kilogram is equal to approximately 2.2 pounds. All right, so calculate the total mechanical energy at the peak height. All right, so what do we have? Let's write down the given pieces of information in here. So we have some kind of a medical device. Okay, I'll just draw it as a box, okay, which is the most convenient, of course, to do. And then in that case, so let's imagine here we have the floor. Now it's telling us that we are, so within here, so it looks like this is the height, which is 285 centimeters. So I'm going to change that back into metric standard, which is going to be 0.285. And that's going to be 2.85 meters. Now, we have the mass within here, or we actually have the weight, so I have to be careful there. So we have the weight, which is 1250 pounds, but because they give us, so within here, notice that they give us the conversion, so I can actually convert this back in utilizing this conversion ratio. So let's see what that is in terms of the mass. So 1250 and then divided by 2.2. Okay, so that's 568.18. I see the repetition there, so I'll just leave it at that. This is in kilograms. I'm not going to round anything, at least not yet. So the mechanical energy that we would want to be able to solve for, mechanical energy is equal to the kinetic energy plus the gravitational potential energy. Now this is of course on the assumption, okay, we're kind of neglecting resistances throughout. So in here, there is no kinetic energy, at least not at the peak, because this thing is just being held up there, right? So we don't have any information in terms of this thing moving at all. So this kinetic energy, well, that's going to be zero. So the only component is the gravitational potential energy, which is just mass times gravity times the height, okay, that this object is at. And that is not very difficult for us to do, especially now that I have the mass there. So that's going to be mass. We'll assume that it's 9.8 meters per second squared for the gravity, and then the height is 2.85 meters. So that is it. Okay, so that's all that we would have. I deleted it out of here, so let me put that back in. 568.181818. You can put a few of those in there times 9.8 and then multiplied by 2.85. So that's going to be 15,869, etc. And this is joules. If you want to round this, I'll round this to three significant figures. So this is going to be 15900 joules in terms of the mechanical energy, because there's no kinetic energy. So that would have been the first component there. Now for part B, it says if the crane chains would break and the device would get into free fall, then what amount of kinetic energy would be present after 0.15 seconds? Okay, so neglecting air resistance. Well, if we want the kinetic energy now, then this is going to give us a little bit of work. Okay, I'm going to just make this much smaller here, okay, so that I can work on the second component. So for kinetic energy, so this is at a time, so a time passes of 0.15 seconds. Okay, so the crane, I guess, was holding it up. Okay, and there was two cranes, so maybe two chains, okay, in there, and these things broke. So this thing starts to fall down. And we want to be able to know how much kinetic energy it has. And that kinetic energy is 1/2 mass times the actual speed that it's moving at. Now, the speed is at 0.15 seconds, right? Now, we do have the mass, at least we have it from the first component. I don't have the speed, but we can certainly find that out. So that's just from kinematics, right? So we have the final speed equation is equal to the initial speed plus the acceleration times the time that passes by. Now, we know all of these. The initial was actually 0 because we started off and the cranes were just holding this up. Now, the acceleration, now this, I'm going to assume, of course, that this is downwards. Okay, I'm going to assume that it's with respect to down. So the acceleration is 9.8 because that's just gravity, and then the time would be 0.15. So that would have been my speed. So this is going to be 0.15 times 9.8, and there's my speed. So it would have been 1.47 meters per second in here. Now that I have this, I can find out what my kinetic energy is, okay, right here. So my kinetic energy is going to be 1/2 my mass, which is 568.18, etc. And then this speed, which is 1.47 squared. So let's do that. Now, since I have this already on the calculator, I'll just put the square. I'll multiply, so I'm going to go in reverse, 568.18, etc. And then times 1/2. So that's going to be approximately 613.89, joules. Again, to three significant figures, this would have been approximately 614 joules. So that's what we would have right there. All right, so with respect to part B. Now let's take a look at part C here. What is the total mechanical energy at that point? So if you're looking at the total mechanical energy, so that's going to be all the gravitational potential energy still remaining, and then all the kinetic energy. Now explained by using the law of conservation, and then by confirming, I guess, with calculations. All right, so well, the calculations is going to be a little annoying, but using the law of conservation, this actually is very simple to do. So again, I'm going to just kind of shrink this up just so that I have a little bit of space there. So this is for part C. So mechanical energy, we know that this remains constant through the kind of flight, well, in this case of this medical device being dropped down, okay, assuming that we have just kinetic and gravitational potential energy. So those are the two that the energy is transferring back and forth from. So if we know what this is, right, which is already calculated, so that's fine. We don't know exactly what the gravitational potential energy is. Now, we do know, actually, because of the law of conservation. Now, the total mechanical energy is going to have to be exactly the same thing as what we started. So, it's going to be, 15, 8, 6, 9, whatever joules. So that's going to be just by the law of conservation, because this amount, so the kinetic energy, was just transferred. So everything was in the gravitational potential energy, and about 614 joules transferred into kinetic energy. And the rest is actually gravitational potential energy. So that's what we would find. Now, within here, so that would have been using the law of conservation. So we know that that remains constant throughout the entire flight. All right. Now, if you want to be able to do this by calculations, well, we've already calculated this, so we have that right there, but we haven't calculated this. Now, in order to find this, this is mass times gravity, right, times the height, which is still remaining. Now, this height is after it has fallen, right, within here. So this is a little trickier because this box, okay, is going to start to fall, and it's going to fall, ever so slightly. And now we want to be able to know, okay, what is still the height which is remaining? So what we need to know what the displacement is. How much did it actually fall from the top and to the point where it's 0.15 seconds that has passed by. So in order to do that, so my kind of the easiest thing, I guess, to do, we have the initial speed. We do have the final speed because we calculated it out, okay, so within here, so that was approximately 1.47 meters per second. And we know the total time. So please remember, again, this is from kinematics that you can use. So this is going to be V initial plus V final, right, divided by 2. So this is the average velocity. And then this is times delta t. And this is going to give us how much it actually has fallen. So let's calculate that. So, well, 0 plus, so 1.47, that's our final. We're going to have to divide this by 2. And then we're going to take our answer and multiply it by, well, this is a very tiny amount. So it has only fallen, because it just basically started to fall, approximately this much. So it's fallen really just about 11 centimeters down. Now, this is not your height. This is how much it has fallen, okay, within here. So that's this right there, okay? But we need to know, okay, this from here to here. So what that would be is we would have to take the original, right, which is 2 meters 85, okay, that we would have, minus this. So since I have this already on the calculator, you know, put minus, this is 2.85, hit equals, okay, so this is how much still remains to be able to fall. Now, of course, it's negative, the negative just means because I subtracted from 0.11, etc. So that is my h. So if I wanted to write this out, this is what it would be. So the mass that I have multiplied by the gravity and then multiplied by this height, 2.7. I'm not going to round anything in here. And now I can actually do the calculation. So I can take this, okay? Now, again, please remember, it's positive height, okay? I'm just keeping it negative on the calculator here. So because I don't want to re-input the numbers. So times 9.8 times 568.181818, etc. So that would be, 15, 255.4, okay, etc. joules, okay, of energy. Now, we said that the total should be this, right? Now, this obviously is less than that, but this is just the gravitational potential energy. So if we would take this number, so I'm going to just clear it, and then we would add it up to our kinetic energy in here. Now I'm going to just do the rounded numbers now. So 614, plus 15,255. So notice, okay, so what it gives us, it's exactly, okay, what we had over here, right there. So 15,869. And that actually proves, okay, that exactly you can do this. Now, did you have to do all of this? No. The question just asks, so it's a mean question because it says, calculate it. By the law of conservation, once you know this, right, you know what you started off with, you could have just subtracted this from that and you would have found out this exactly. This is the long way to do it. All right, so that is it for this example. In this next example, so it says, outside of mechanical energy, what other forms of energy can you think of? Okay, describe them in a few words. All right, so I'm going to take a cop-out on this one a little bit, okay, and I will refer you to a video which I made with regards to the forms of energy, and I'll put up a link up above there, okay? I believe that that will help you a lot, okay, in terms of answering this particular question. All right, so that's all that I'm going to say here. Here's the next example where it says an ambulance is tending to an emergency. The ambulance is speeding at 125 kilometers an hour. If a typical ambulance has a weight of 11,000 pounds, then what is the vehicle's kinetic energy at that speed? All right, so for kinetic energy, in terms of thinking, we need this particular formula. So it is 1/2 times the mass times the speed squared, and then we know how much kinetic energy an object actually has. Now, they do give us what the speed is in here. So this is 125 kilometers per hour. Now we're going to need to change this into SI units. So let's do that. So in terms of converting this back, okay, so I'm going to take out a calculator, so 125. So now, okay, I'm pretty used to this conversion, so it's going to be divided by 3.6, okay, in order to get what the speed is. So that's 34.7 and a bunch of 2's, and this is now meters per second. What I'm doing is I'm changing kilometers to meters, okay, and then I'm changing hours to seconds, right? So I'm doing the unit conversion there. You can certainly do it in the longer way if you like, okay? So this is a very quick way. If you remember, you can just simply divide by 3.6, and that will get you to meters per second. So it actually converts, okay, that's the conversion between 1 meter per second and 3.6 kind of kilometers an hour. All right, so that's the first item. Now, the second item is they do give us what the weight is. Now, it's not very convenient, and this will depend on which of the actual conversions you remember. So if this is 11,000 pounds, we can certainly change this back to mass. Now, I do remember, okay, so the conversion is that 1 kilogram is equal to 2.2 pounds approximately, okay, in terms of that conversion, right? So you can certainly use that. You can use other conversions, for example, converting it to newtons and then dividing by 9.8, and you'll get the same thing. So within this conversion, what I'll do is going to be 2.2 pounds, and that's per every single kilogram. So that's going to give us what we need in terms of mass. So let's do that, divided by 2.2, so that is, okay, so about 5,000 kilograms. So, you know, it's about 5 tons, okay, in terms of mass. All right, so now the kinetic energy component, well, so if we take 1/2 of, this is 5,000, and then this is going to be 34.72, okay, and this is squared. That's going to give us what the result is. So I already have this on the calculator. Okay, so I'm going to take half of that, and then I'm going to multiply by the speed, which is 34.7 and a bunch of 2's, and then I'll square that equals. So this is approximately, so 3 million, okay, and this is 14,081 joules. So it's quite a bit, well, especially since you are dealing with quite a big, okay, so in terms of a vehicle. Now, if you want this rounded, let's say to 3 significant figures, this is going to be 3, 0, and I guess just 1, 0, 0, 0, 0, okay, joules. Now you can round to whatever it is that you may need, okay, from your teachers. But that's all that you would actually have to do in this example, all right? So that is it. So here's a neat one. So it says a set of 5 incandescent light bulbs are used in a medical testing lab. The test takes 35 minutes to complete. Each bulb is rated at 50 watts, so this is power. If the test has an energy efficiency of it's 4.2%, so it's not that very efficient, then what was the total useful energy utilized in the test? So this is going to kind of bring you towards energy efficiencies, okay, so and so what that means is that the energy efficiency, and this is as a percentage, is equal to the energy which you actually output, and this is the useful energy, divided by the energy which you input, okay, which is the total energy you need. This is times 100%, and it's going to get you what the efficiency is. So this is really, okay, what the utilized, useful energy is. And unfortunately, most of the time when we put in energy, it is transferred into energies that we don't actually need for the application. So even if you are, turning on your TVs, your devices, you're driving in cars, we're not super efficient, okay, in utilizing what the energy that we're taking in. So some of it is not going to get transferred to exactly what we want. Now, with this formula, so we can certainly solve this example. Now we need to try to figure out what we actually have given. So first of all, we do have this, right? So with regards to this example, so this right here, this is 4.2%. So I know what that is. And what else do I have is I have power. Now, let's take a look here. So the power of the bulbs, it says, is 50 watts, which really is, 50 joules per second, because that's what a watt is. Now, recall that power is equal to the energy divided by, or the work, divided by the time, right? Or the change in time that we have. So therefore, if you want the energy, you can certainly take the energy, and it is just equal to the power multiplied by the change in time. So, we can certainly do that. Now, we have 5 incandescent light bulbs. So, this 50 joules per second is going to be multiplied by 5 because we have 5 of these, right? So this is going to be approximately 250 joules per second, right? So that's 5 of these. Now, we need to multiply it by time to get the actual energy, right, that we would have, so the energy that we're inputting. And that particular time, so they do tell us, is 35 minutes. But of course, we can't just multiply by 35 minutes because we need this in seconds. So I'm going to just convert this. So this is 60 seconds per 1 minute. Right, so the minutes cancel, and I know how many seconds, and notice with the units, the seconds will cancel as well, and we're going to get, the amount of energy that we have. Now, this is the energy that is being inputted. So, the light bulbs are taking in 50 watts, right? So every second they're taking in 50 joules in order to get, be lit, or whatever it is that they're doing. But we're only 4.2% efficient. So let's take a look, okay, and try to see and calculate this whole thing. So this right there, okay, so as it stands, so let's try to do that, is equal to, so I'm going to put that in here on the calculator, so it's 250 multiplied by 35 multiplied by 60. So that is the total. So it's quite a bit of energy, okay, that we have over that 35 minutes. And that is your energy that is inputted in, okay? So if that's the energy inputted in, so now all of a sudden you have to now solve, okay, for this, because that is the energy, the useful energy, okay, that we have. So how do we get this? Well, this is 4.2%. This is 525,000 joules, right? So we're going to take this, we're going to multiply it by this, okay? This 100%, okay, is going to disappear. It's going to remove the percentage from here. So let's do that. So let's take this 100 and then divide it by this side. So obviously 4.2 is just 0.042. When you divide by 100, that's the decimal equivalent. Now we take that and then we multiply it by the energy, which is 525,000. And there you go. So what you would have is therefore that this energy out would be, much, much smaller in terms of the useful energy that we're actually getting out. Okay, so from whatever lab device this might be. And that would have been your final answer. Now, if you want to round it, you certainly can. If you're rounding it to 3 significant figures, then it would be that right there. Okay, or again, you can, leave it to whatever it is that you're being asked to do. Okay, so that is the example. So this example just follows. It's a good one because it introduces you to efficiency and understanding that unfortunately we're not very efficient in most of the things that we utilize energy for. Okay, even for our own system. Okay, so there's much of the energy goes into not necessarily waste, but it just gets converted and transferred to something different. All right, so that is it for this example. Here's the last example for us with regards to this. Again, it looks like it's the calculation of power output. Okay, so what is the power output of the runner? It gives us a few pieces of information. So a runner transfers 350 calories, okay, of chemical energy into kinetic and thermal energy in 18 minutes. All right. So now we want to know what the power output is. So first, we of course have to know that power, okay, is the energy, okay, over the time that passes by. Now we have all of this. This is actually 350. However, it's in calories. And this right here we have also, which is 18 minutes. So our only hiccup really is, the actual unit. So we're going to have to kind of change the units, okay, into what we need, into SI units. So if you start, so this is going to be 350 calories. Notice they give you the conversion. So 1 calorie is 4184 joules. So that's going to give us that. So I can take that in. So 350 multiplied by 4184. So that's 1,464,000. And this is 400. This is all in joules. Okay, so that's quite a bit right there in terms of joules. Now, in terms of 18 minutes, well, 18 minutes we can certainly change back to seconds. So that's not very difficult for us. So that's 60 seconds per each one, right? So that's going to be 18 multiplied by 60. And there we have, this is going to be the number of seconds, right? So kind of that passes by. All right, so now if we substitute these two particular numbers, so this is for the energy, this is for the power, our answer is going to be in SI units. So the power is equal to, so let me plug all of this back in. So 1464400, and then divided by 1080. And so there you have it. I'm gonna just round this off, okay, to 3 significant figures. This would be watts, okay, or the wattage, right, that you have. So in this case, this is actually 1.36 kilowatts that you have. All right, so that is it. Thanks for watching. See you in a future video. Bye, everybody.